Welcome to Lesson 9D, Room Ventilation with Recirculation. Today we're going to talk about recirculation, which also involves what we call makeup air and makeup air fraction. I'll define those terms as we go along. We've already done some recirculation. If you remember, we had a situation where we had a room and then we added an external air cleaner. We just drew air out of the room and then put it right back in through an air cleaner. And you have to have some kind of a fan or a blower in order for this to work. Now, when we have this forced ventilation, we want to have the air that's coming out exhausting through the ventilation system to somehow go around and come back into the supply. What we'll do is this: we'll take this air that's coming out and we'll take it around here. This is just a schematic. This is happening in the attic, under the floor, or wherever. We'll put our cleaner in here, and then we'll come to our fan, and then we'll have it go back up. So it's the same thing we just did back here previously, except now we're using the ventilation system itself. Now it's part of the HVAC system. This is what we call recirculation. What we want to do is introduce some makeup air. This will be the bottom T. Makeup air will have volume flow rate QM. We're drawing this from the ambient air, so it'll have a concentration of Ca, just like the infiltration is coming from outside. We're going to combine that with the flow coming from the exhaust. We'd have some Q1 going into the cleaner. And what is that Q1 and what is that C then? You're now mixing C from the room with Ca. That's why we have to worry about how to handle T's. Makeup air is defined as fresh air from outside, mass concentration Ca, that we put directly into the HVAC system. If we do a bulk air balance, we have this bottom T here, Q1 is equal to QE plus QM. This is QE coming down here. QS, the supply coming in, plus Q infiltration equal QE plus Q exfiltration, just taking all the inlets of bulk flow air. And I forgot to say also that Q1, since it's going through this cleaner and fan, if there's no leaks, Q1 has to equal QS. So that's why I'm setting that equal to QE plus QM. That's QM plus QINF equal QE plus QEXF. And you see that these two cancel. And so we have QEXF equal QINF plus QM. So in other words, we're forcing some extra flow to come in, and not all of this flow that comes in supply gets exhausted because we're adding QM to QE, bringing all that in. So QS has to be bigger than QE, and therefore QEXF has to take up the slack. So it will be greater than QINF. So the Q exfiltration is bigger than the Q infiltration. And so this situation is unbalanced. You would have a high P in the room that will force extra air to go out. How do we balance this thing? Well, we have the same thing I just had, but I've added this part up here. We also are allowing a discharge. So now I have two T's. We have the top T and the bottom T, and we have a discharge. QD is the discharge volume flow rate. And so now let's balance the system. So we're going to force QS to equal QE, which we can call Q the overall Q. So that's balanced. And QINF equal QEXF. Infiltration and exfiltration are the same. So that's balanced with the bulk air. We split the Q into two parts. So that's why we have these T's. On the top there, QD is the volume flow rate of discharged air, and that's equal to F times Q. CD is equal to C of the room, since it's just coming straight out of the room. This top T doesn't affect the concentration at all because you have C coming in. It splits into C going this way and C going that way. This F is called the makeup air fraction, the portion of Q that goes into QD, the discharge. The second part is QR, which we call recirculation, the volume flow rate of recirculated air. CR is equal to C because, again, we haven't done anything to the concentration by splitting it off like this. F is equal to QD over Q. And if we do a bulk air analysis for the top T, we have Q equal QD plus QR. We're just splitting it into QD and QR. And so Q is equal to, from this equation up here, FQ plus QR. And we can solve for then QR is equal to 1 minus F times Q. So some portion of it goes to discharge F, and then the rest of it, 1 minus F times Q, goes to the recirculating air. Now, as far as the outside air goes then, this is a balanced system. And so notice that QM is also equal to FQ. QS has to equal QE. So if I'm taking out FQ there and I come around, I have to add FQ from the outside air back in order to keep QS equal to Q, and the same as QE. For the balanced case, QM equal QD also. Think of this as the wall of the building and you have some kind of an outlet, QD, and from the air's point of view, you have the same amount of makeup air coming in. So QM is also equal to FQ, and that's what we call the makeup air. In other words, we define F as the makeup air fraction because QM is F times Q. Now let's look at the bottom T. We have QR coming in from the top, we have QM coming in from the left, and then we combine into QS or Q. What is C1? That's what we need to calculate. Well, we already talked about T's like this, so we know how to do this. We have a QR, we have a QM, and we have a Q on these three branches. The concentrations are C, CA, ambient, and then C1 is what we want to find. Bulk air, QR plus QM equal Q. And then we know that QR from up here is 1 minus F times Q. So we plug that in. QM was equal to FQ, and that's equal to Q.
But, sir, that equation reduces to Q equal Q.
You're right, Boris. That's because of how we defined F.
Thank you, sir.
And then if we do the contaminant mass balance, we have CQR coming from the top plus CAQM coming from the right equal C1Q. And now we should be able to solve for C1. C times 1 minus FQ plus CA times FQ equal C1Q. The Q's cancel. C1 is equal to C times 1 minus F plus CA times F. Now we have C1, and what comes next is a cleaner. We're going from C1, which we now know, into this cleaner. Well, we know what the equation is across the cleaner, knowing eta. Through the cleaner, we have the same Q, assuming no leaks. We have CS now. Go through the fan, again, assuming no leaks. We push that into the room, so that's what we're calling QS now, or just Q. So the air cleaner, recall C out for a cleaner is equal to 1 minus eta times C in. And so here, the outlet is CS and the inlet is C1. So this is the equation across the cleaner. And now we plug in that for C1. And now we have an expression for CS. One of the goals is always to find CS. Once we know CS, we know how to solve for this room now. This is old hat now. Look at sources and sinks of contaminant into and out of this room or building. VDCDT, it's always the same. We start with that. We put in all the sources, then the sinks. Now you're tempted to say, oh, divide by V, and then this whole group is B, and this whole group, if you divide by V, is A. But that's not true. It gets more complicated because we solved for CS, and CS contains some terms with C and some terms without C. So our next goal is to plug in that CS and separate all the terms that have C in them and all the terms that don't have C in them. So let me rewrite this. You can see all I'm doing is plugging in that equation for CS, and that's multiplied by Q. Then the rest of it is the same. Remember, our key is to separate terms without C and with C. So I'm going to put a box around all the terms without a C. I'll put squigglies under all the other terms. They all have a C in them. Don't forget to multiply this first term also times Q. So we'll just put these in our standard form then. We have our negative sign in this equation already, so be careful with your signs. So this is B, and this is A. And then CSS equal B over A, etc., like all our other problems. Let's do an example. This is identical to previous problems. I just keep adding some new features to it. Here we have recirculation now with makeup air. I give you all these parameters, and these are all identical to previously. Notice that we don't give a CS. This is what's different from before. We had to give CS because we didn't have any of this recirculation stuff. Here, CS is not given because we have to calculate that based on all these other parameters. But everything else here is the same. Now we have an air cleaner, so we would write eta is equal to 0.945. Don't use percent in your equations, use the number. Also, F is equal to 0.15. We want to find the steady state mass concentration. It's the same numbers as the previous example. Now I took my B and my A from here. You take B over A to get CSS. The V's cancel, which they always do in these problems. And so now I have an expression for CSS. And so when you plug everything in, you get CSS is 1.1188 milligram per meter cubed. And so to 3 digits, I'll give my answer as 1.19 milligram per meter cubed. Some comments. We specified F in this case as 0.15. Well, how do you set that? How do you do that? The answer is to use dampers. The damper is like a valve, and you could put one here, for example, and you can put another one here. You adjust these dampers until QD equal QM equal FQ, and this F is the desired F of 15% in this case, if that's what you want. If it's not balanced, QD will not equal QM, and therefore Q infiltration will not equal Q exfiltration. If these two are not balanced, and that's the only things coming into and out of the room ultimately, because we have recirculation of everything else other than infiltration and exfiltration. So one of these is going to have to be bigger than the other if this is not balanced. That's not always a bad thing. Sometimes unbalanced is done on purpose. For example, in a hospital room, suppose you have a person with a very contagious disease, Ebola, tuberculosis, COVID, and you have that person in a bed in a room. The worst thing you could have is to have the room be pressurized so that you're going to get some exfiltration. Suppose this is a room within a hospital and you would get exfiltration under the door, for example. So you would have bad air, contaminated air going out into other rooms or into the hall. What we really want, you want the P of the room to be less than P outside the room, so that if anything, you're going to get too much infiltration compared to exfiltration. And in fact, we would want it so that Q exfiltration is actually 0. And so you keep pressure low in the room so that you're not going to get any exfiltration. This will actually turn around and come in the other way. So you'll get some infiltration, getting clean air into the room. And then what do you do with this discharge? You can send that up a stack, a chimney, to get it out of the way, or you can send it to some kind of a cleaner. Ultraviolet lights kill a lot of germs. Send the discharge someplace that's not exposing people. My second comment, let's compare to previous examples. And I purposely did the same numbers, the volume and the contaminant concentration in the outside air and S. All these numbers are exactly the same as before. We can now compare these different CSSs for various types of these problems. So module 9D is this one, the one I'm doing right now. We have recirculation, a cleaner, infiltration, plus wall losses, and we get CSS is 1.19 milligram per meter cubed. The one we did previous to this, module 9B, we had an ERV, an energy recovery ventilation unit, plus infiltration, wall losses. We had a source in all these. I'm not going to list all that. There was no recirculation and no cleaner, and CSS was 1.00 milligram per meter cubed. Why is this one better than the one we're doing now? Well, in the one we're doing now, we didn't have an ERV. We are bringing in some fresh air from outside. It's just like we do with an ERV, the CA. So that part's kind of similar, but the flow rates are very different. We specified CS kind of arbitrarily, 1.56 milligram per meter cube, a number that I pulled out of the hat, so to speak, Whereas here, CS is calculated. It's not just arbitrary. And we specified the ERV flow rate, QERV, which was 100 CFM. We're getting a lot of fresh air in there. If I would pick different numbers, I can get this to be bigger or smaller. If we go back further, module 9A, that one had infiltration and wall loss, but there's no cleaner and no recirculation. So we would expect this one to be worse. And in fact, if you look back, CSS was equal to 1.74 milligram per meter cubed. So when we added the ERV to this case, we got much improvement. And then finally, the first time I did this particular example with these numbers was 8D, where we had the same air cleaner that we have now. I specified the same ADA to make this a good comparison. We have the same wall loss, but of course we have no recirculation, we have no ERV, we have no infiltration because we hadn't learned about infiltration back then. But the infiltration helps. It doesn't help your pocketbook, but it helps CSS. When you have no recirculation, you have no makeup air, except if you have infiltration. Here we have no ERV and no infiltration, so CSS was a lot higher, 2.63 milligram per meter cubed.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.